How you doing? I'm Mr. Rose, and today we're going to talk a little bit about angular momentum, more specifically conservation of angular momentum. Now, I've said a lot of times that all of our rotational physics, essentially is the same thing as translational physics. So conservation of momentum and conservation of angular momentum are two very similar concepts. It just happens that one of them is rotating, one of them is not. So here, hopefully you can see this. This is a question that comes out of a book, Holliday, Resnick, and Walker. It's the Fundamentals of Physics. It's an 8th edition. As you can see, it's number 57, and that's from chapter 11. Chapter 11, I think. From this picture here, you can see, like I said, read the question. As always, I do recommend you try to do this problem before you watch me solve it. I'll be running this cold, so hopefully we get to the right answer. And you can kind of see a thought process as we go. Anyway, we see this bar right here. This bar is rotating about the central axis, and this ball of mass m, it's not a point particle, but it's just some ball, mass m, starts stuck to the rod, and then as this rod starts rotating, or continues to rotate, whatever it was doing, this ball is going to get ejected off. And what we want to know is, if the particle speed, Vp, is 6 meters per second greater than the speed of the end of the rod just after ejection, how fast is that particle going, Vp? So that's what we're looking for. Essentially, this is going to be a conservation of momentum problem. So I am going to move this up now, such that you might not be able to read the question. And we're going to start talking about exactly what we're doing. So like I said, it's going to be some kind of a conservation problem. And that is terrible. I will write neater than that. It's going to be a conservation problem, but this is going to be a law. This is a conservation of not linear momentum, but of angular momentum. So it's a conservation of angular momentum problem. So the things that I know from my question is, rewind and back that up. We knew there were 3 types of collisions in linear momentum, or interactions as I call them. One of them was an explosion. I'm going to imagine this kind of as that same thing, because this particle starts as seemingly one object, and that looks really annoying with my, there we go. This particle starts as seemingly one object, and eventually it's going to explode off, get flying off. So that's why we're trying to imply this conservation of angular momentum, and I'm going to kind of think of it in that translational sense as an explosion. So what are the things I know from this problem? Hopefully you start listing some variables. So the things I know, I just got to look at the camera so I'm not writing on my face. The things that I know, I was given the length of the rod. The length of the rod, actually I don't want to use a capital L because that's our angular momentum. I'm going to say the length of the rod is a script L, and the length of the rod was 0.800 meters. I know the mass of the rod. I'll use it to say mass of the rod. I'm just going to say is a capital M. Let's see, other thing. I know the angular velocity, omega, of the rod was 20.0 rads per second. I know the particle, the mass of the particle is actually big M divided by 3. So the rod itself is, or I should say the rod itself is 3 times the mass of the particle. That was given my problem. I know, what else? I know this is going to be important. I know that they told me that the velocity of the particle is equal to 6.00 meters per second faster, so plus the velocity of the end of the rod. I believe that's all the information I knew. I said initially the particle was stuck to the rod. We got that. So this is all the info I know. How am I going to handle and what exactly am I going to do with that? Well, I know according to the law of conservation of momentum, this just happens to be conservation of angular momentum, I know that my momentum before has to be equal to my momentum after. Again, oh, sorry about that. Try that again. My momentum before, there we go, has to be equal to my momentum after. I'm going to start a new page. Just so I have more room to write, and I'll start to write a little bit bigger. But my momentum before, now again, this is going to act as an explosion. An explosion, the interaction, is seemingly two particles acting as one. What are those two particles? I have that little particle stuck to the end of that rod. Particle is a mass or an object, and the rod is an object, but these things are stuck together. So, move that out of the way so I have it. I have all my givens up there. I'm going to say initially I have the angular, oh, that is a bad spot for me to write. I have the angular momentum initial equals the angular momentum final. Now, initially I have, just going to go right under, here we go. Initially I have the angular momentum of the particle plus the angular momentum of the rod. That's going to equal the angular momentum of the particle after the explosion, which I'll designate as a prime, plus the angular momentum of the rod after the explosion. All right, well, what is that angular momentum? Remember, there are two different ways to calculate angular momentum. It is I omega, or it is r cross p. Now, while this particle is stuck to my rod, I can't treat it as just some particle because that rigid rod, I can draw a picture here. There's my axis of rotation. I'll throw this purple particle here. This rod is rigid, so I can't ignore it. So I need to treat that particle a little bit differently. It is, let's see, the moment of angular momentum is I omega. It's going to be the moment of inertia of that particle times the angular velocity of the particle plus the moment of inertia of my rod times the angular velocity of the rod equals I particle omega particle prime plus, now this guy, I'm a little hand wavy here. We're going to get back to that. Plus my angular momentum of the rod is going to be I rod angular velocity of the rod prime. Now, hopefully, or I shouldn't say hopefully, you might not have this guy written down, and we're going to get to that momentarily. I'm going to first work with my initial conditions. The initial conditions seem to be easiest. Now, my moment of inertia of a point particle, or this particle of mass m, that's easy. That's just mr squared. Now, omegas, all of my omegas are the same. My initial omega and my final omega have to be, these two are the same because they're rotating, and those two are the same. So this I'm just going to designate as omega naught plus my moment of inertia of the rod rotating about the center of the mass. That is going to be 1/12 m. Oh, that should be a script EL based on my ml squared times omega. Again, I'm going to ignore my after right now. Now here, my particle at some radius for rotation, that's going to be the mass of the particle times script L over 2. That is half my rod, and that's squared, times my initial angular momentum. Plus, I didn't do anything here. This is still 1/12 capital M L squared omega. And actually right here now is a good time to start talking about the other side. Now the other side, I was kind of lying when I have this I omega squared, because afterwards this particle is ejected. Now, if you remember, the angular momentum of a particle that is free spinning, no longer attached to that, is an I omega. That's why I circled it. I lied a little bit here. This should actually be not I omega, but this should actually be, think about it, think about it, think about it, R cross P. I know I wrote that super small, R, because now this is a particle that was in rotation. I'm talking about that very moment it is leaving, so it was still in that circular motion. So now R cross P, that's just the radius away times its linear momentum, right? So instead of I omega, I'm still going to have, what am I doing, R times the mass of the particle times the velocity of the particle. That is my, notice I lost my cross product. When I lost my cross product, that's because at 90 degrees, R cross P is RP sine theta. Sine theta is going to be 90. So clearly that's just R times M times P. Now plus nothing happened over here. My final momentum is, angular momentum is still 1/12 mass of the rod times omega, 1/12 M, not mass of the rod, sorry, times L squared. That's my I. So see what I did there? I no longer have this particle attached. It's moving linearly. So my conservation of angular momentum has to be that moment it is unattached. So I'm calculating its angular momentum of a particle, R cross P. Now R is still L over 2. So I should have the mass of my particle times the velocity of my particle times, this is my momentum of the particle before, my momentum of the rod before, both angularly, momentum of the particle after, momentum of the rod after. So now from here we can start hopefully subbing some things in. Let's see, my momentum beforehand, I have L squared over 4, so I'm going to say 1/4 mass of the particle times L squared times omega. Plus, now I want to start simplifying terms. I know from my initial condition, mass of my particle is the mass of the rod divided by 3, which means I can say this mass of the rod, I can say 1/12 times 3 mass of my particle. That whole thing times L squared omega equals, right? So that is everything beforehand. Now after, this guy looks like it's going to stay the same. MV, yeah, that stays the same. MP, velocity of the particle, L over 2, plus 1/12. And again, I can sub in my 3 mass of the particle, 1/12 mass of the particle, times, I dropped the square there, times L squared, omega. Let's see, now I can start to simplify terms. And here I'm going to have, I like what that looks like, equals, now afterwards, I'm going to have, not a lot of simplification here. I'm going to have my mass of the particle times the velocity. Let's see, what did I do here? Mass, let's see, I'm going to cancel that. That's going to be a 4. Mass of the particle, velocity of the particle, times L over 2, plus 1/4 mass of the particle. Oh, that's squared. No, that's the radius, that's not squared. Mass of the particle, L squared, omega squared. And now, that was why I paused. I knew something was going on. Mass of the particle, mass of the particle, mass of the particle, hey, look at that! Mass of the particle is now gone. So now I'm going to have this nice little equation. I'm going to flip this because I know what I'm looking at right now. I'm going to bring my final side over here. So I'm just changing the order. I have momentum final equals momentum initial from this point on. Because that's going to make a little bit more sense. So I have now that mess looks to be a bit of a mess. It's actually not. This is going to be super helpful. I'm actually super happy right now. How is this going to be helpful? What are the things that I know right now? I know VP, but I know VP in terms of variables. I don't know exactly what it is. That's, remember, what I'm trying to figure out. I know the length. I don't know omega prime. So it seems like I have two unknowns here, and I know the initial omega. It seems like I have two unknowns here, so I've got to think to myself, do I really have two unknowns? And the answer to that is no. I can figure some stuff out about omega prime. What are you talking about, Mr. Rose? What the heck can you figure out about omega prime? Well, let's see what I'm going to copy that onto my next page. All right, so what can I figure out about omega prime? Well, if you recall things, Mr. Rose, how do I get from omegas, angular velocities, to linear velocities, translational velocities? This is important, I'm going to write it up here in purple. If you want to recall, I told you to memorize three different equations. Those three equations, one of them was V equals R times omega. If I'm trying to memorize V, how is it? Wait. How is that helpful? I know that this would be the same thing as prime, which means I can now say V particle times L over 2 plus 1/4 the length of my rod squared. Omega prime, this must be V prime. I'm not going to call it V prime. I'm going to say omega prime was omega at the end, the angular velocity at the end, which means this must be the velocity at the end divided by R, and we know R is L over. Those two things are equivalent. My initial condition. Now, the problem told me that the velocity of the particle is 6 meters per second faster than the velocity at the end, which means I can say the velocity of the particle times L over 2 plus 1/2 times L squared times the velocity at the end is really the velocity of the particle minus minus 6.00, meters per second, divided by the radius, which was L over 2. That whole thing is going to be equal to, and does that look like a nice, pretty, but really not so pretty kind of ugly equation, right? V particle, L over 2 plus, I knew that was wrong. That should be 1/4, that should be 1/4. 1/4 L squared that I got there. 1/4 L squared times my omega prime. That is a beautiful, beautiful thing. Now, what do I start to do? I believe I can start to simplify here. L over 2, 1/4. Okay, so to simplify that out, sorry, I had a brain fart here. This is, I can cancel this L with this L, and that will become 1/2. So I should have V particle times L over 2 plus, it'd be 2/4, but 1/2 L, so I got rid of my squared, times V particle minus 6.00 meters per second equals 1/2 L squared times omega. Which means now I can say that V particle L over that is 1. Oh, I can do that. VP L over 2 plus L over 2 times V particle minus 6.00 meters per second equals L squared over 2 omega. L cancels, L cancels, L cancels. You probably saw that before I did. So now I have 1/2 V particle plus 1/2 times V particle minus 6.00 meters per second equals 1/2 times omega. Omega, which was 20.0 rads per second from my initial conditions. And that means I can solve for VP. Yeah. 1/2 VP plus, I was going to use my calculator, but I'm just saying plus 1/2 VP minus 3.00 meters per second equals 10 rads per second. Distributed that, add that, that's going to be 13. 1. Oh, wait a second. Oh, I dropped my L. You didn't drop your L. I dropped my L. Times the length of my rod, which is 0.80 meters. All right. So now that is 10. That is 8. That's going to be 8 rad meters per second. Oh, that's good. Right? Rads per second times meters is 1/2 is 10. 10 times 0.8 is 8 meters per second. Meters per second. 1/2 plus 1/2 is the velocity of the particle at the end of the rod is 8, 9, 10, 11.0 meters per second. Woo! Anyhow. That's all I have for you today. I hope this was helpful and you could see how I approach the problem. Now, I talk way too much. Hopefully you solved this, and if you didn't solve it, you saw how I did it. I'm going to not edit out any of my mistakes. I'll speed up, and you'll probably see that. I sped up some of the quiet time or the thoughts going through my head time. Again, hopefully you saw those things a little faster than I do. The camera makes me a little nervous because I don't want to make any mistakes. Please feel free to like, comment, or subscribe. Sorry, like, comment, and subscribe. And just keep on keeping on. Okay, I'm going to edit that part.